Okay, so as one of the seniors here and as the last speaker, I take the liberty to think a bit more extensively. So I was told by many of the senior people that they really enjoyed the conference and that they appreciate the mixture of young, fresh mathematicians and more senior people and diverse subjects, and so I think really that the four young organizers, Francesca, Kuhn, Sven, and Joachim, made a really good job. That's one thing I wanted to say. Secondly, I want to mention my co-authors. I made a mistake over there, so I will give. So the goal of my talk is to explain the many words in the title, and I split the talk in two parts. So in the first part, I will review some work I have done in the last in the last decade, in particular with Henry, who is here in the audience, and this will lead to the so-called rearrangement lemma, and then I will take this as an excuse and muse about some surprising mathematical aspects and connections of that to divide differences, which is something from numerical analysis, and the multivariate holomorphic functional calculus, which has a long history, and that's more or less a pedagogical part of the talk, because it's of course old stuff and not at all my invention. And I also mentioned young people. I'm talking with Louis Hartmann from Brazil and Ihan Lee, who was a Hausdorff postdoc here and is now in Ghent. Okay, so let me start with the first part, and that's more an aspect which hasn't been here on the main focus so far. So let me remind you of more spectral theoretic, spectral geometric aspects, also of non-finite geometry, and for that I first remind you of the so-called heat and resolvent trace expansions, which also have a long history. So it's at the foundation of spectral geometry and so-called local index theory. So first here the geometric picture. So you take a closed Riemannian manifold and take a second order differential operator for this discussion. You can take your favorite one, and of course in the background there is a spectral triple if you want. What you can always do is take, say, M, you take the spinor bundle, the Dirac operator, and then you are in business, of course. And so the Dirac Laplacian is an operator to which this slide applies. So, and then I assume that the operator is positive, and so then the heat semigroup is a trace class operator. And now I'm viewing the heat trace as a functional also on functions. So I plug in a function here and I take the trace, and then it has a short time asymptotic expansion. And all what is important is the pattern. Yeah, so you have an asymptotic expansion here in powers of t, and here there appears the dimension of the manifold. Of course, that's a misprint. So between the lines, I said second order. Okay, so this 2 here is the order of the operator, and then there are invariants. I label them with 2j and z instead of j. If you really want to know, ask, and I will explain. Otherwise, I will just shut up. And this depends on the operator and the function, of course. So actually, this invariant is the integral. So it's linear in f. So it's the integral with manifold of f times an invariant of the operator labeled by 2j, and it's just a smooth function on the manifold. And combinatorially, that's very demanding. So with growing j, it's more and more difficult to compute these invariants. That's not my major focus here. I mentioned as an example the two-dimensional case, and this we should keep in mind also for what is coming later. So suppose you have a two-dimensional manifold with a background metric, and suppose you change the metric conformally by a positive smooth function, and then that's a two-dimensional phenomenon that the Laplacian just changes in this way, so the conformal factor comes out here.
Did you fix volume form or you take?
Ah, okay, yes, of course. I'm always integrating. So I said Riemannian. I did not. Yeah, so I was frugal with the notation, of course, when I integrate against the volume measure. So otherwise these objects would be densities. Yeah. So now the first two heat invariants in this case can be computed explicitly. The first one is not that interesting. It's more or less a constant. It integrates to the volume of the manifold times some 2π factor. The second one is quite interesting, and one could tell a lot of stories about this second invariant. So what is important here is with the conformal change of the metric, it changes in this typical way. So here this is the Gauss curve. So that's just a smooth function depending on the background metric, the Gauss curvature. And here the Laplacian with respect to G0 applied to the conformal factor appears. What is also worth mentioning is how is this expansion proved? I mean, not in details, but in principle. So there are several methods, but say that the method which is most relevant also for us maybe is the following. So you write this heat semi-group as a contour integral over the resolvent. Okay, so now the resolvent won't be trace class in general, but you can integrate by parts and put as high powers of the resolvent here as you wish, and then you have a trace class factor there. And then there is a 1-1 correspondence between the short time asymptotic in T of this and the corresponding resolvent expansion as the resolvent parameter goes to infinity. And this allows to apply pseudo-differential calculi to this. And here it is important to apply this so-called parameter-dependent pseudo-differential calculus, which is more than just mentioning that there is a parameter involved. So the parameter is built into the pseudo-differential calculus. A very important aspect. And it works very smoothly for differential operators. It works not so nicely for pseudo-differential operators. In particular, Gihan Li is working intensively on the generalization to arbitrary pseudo-differential operators. Okay, so here this is just the pattern again. So so this expansion and the expansion as lambda goes to infinity can be translated into each other just by standard means of integral transforms. Now, where's the connection to non-convex geometry? I try to give it in a non-technical way. So if I would go into the details of this buzzword here, I would talk the rest of the hour about Heisenberg models. I don't want to do. So I just have a translation table here, short one. We have the manifold, and now, okay, in front of this audience, fortunately, I don't have to say what a non-convex torus is. So, so I take a non-convex torus. But to make things a bit more interesting, also take a vector bundle into account. And now, nice vector bundles on the non-convex torus are so-called Heisenberg modules. I refrain from writing down the formulas. All you need to know for now is such a Heisenberg module, just as a space, is essentially a Schwarz space, or the Cartesian product of a few copies of the Schwarz space, and then you have a bimodule structure with respect to the non-convex torus, and torus with another theta on the other side, and also an R2 action which is compatible with the action of R2 on the 2 torus. And now where's the operator? So here on a vector bundle we have a connection Laplacian usually, and the R2 action on the torus or the Heisenberg module gives rise to a connection, and there is a connection Laplacian. So we have a very nice translation table here, but it's not completely one-to-one. So that it has interesting aspects, namely this the representation here is so the representation of the Schwarz space with values in the algebra is actually a twisted C-star dynamical system, and this causes the difficulty that you have to modify the pseudo-differential calculus, and I have done this in our work for the ordinary parametric pseudo-differential calculus. Again, Bihan Lee extended it to the weakly parametric case, which then allows to resolve expansions in general. So here's a bit more on this situation. So so in the case of such a Heisenberg model, you have n equals 2, so you have a C-star dynamical system over R2, and everything takes place over the Schwarz space with values in the smooth part of the algebra. So the smooth part of the algebra are those vectors where the Rn action is smooth, and the twisting is here. So you have a pure joint matrix and expression, and then you have a projected unitary representation where the twist is built in. And well, so you're essentially in Rn, but with this twist, but you can play the same game in this situation as one does with pseudo-differential operators on Rn. So okay, so you look at Hermander symbols. I'm not going to formally define what this is. So these are functions on Rn with respect in the algebra with certain growth conditions. And then formally, the formula for pseudo-differential operators is the same as usual. So when you so from here to here, this is what you would do in Rn when you set up pseudo-differential calculus. But then the twisting is reflected in the formula here. So the twisting shows up here. So in ordinary pseudo-differential calculus, there wouldn't be any x dependence here, so there wouldn't be this b of x, and this causes certain complications. But nevertheless, you can build a calculus as one does on manifolds. So one of the major is this one. So when you multiply, you get again a pseudo-differential operator. However, as you probably know, when you compose pseudo-differential operators, there is a formula for the symbol expansion of the product symbol, and this symbol expansion in this case is again twisted by this twisting situation. And now, so one sets up pseudo-differential operators not for the sake of setting them up, but to understand differential operators. So what are natural differential operators? Well, that are those operators whose symbols are polynomial. And now you can do this in this setup also just in the same way, and you see that the twisting is reflected by the fact that the ordinary first order different derivatives have the twisting as a potential in their formula. So this twisted C-star dynamical system or the pseudo-differential operators on Heisenberg modules over the non-convex torus are in fact a series of differential operators with potentials of that form, and that also explains to some extent the name, because when you square that, you get the harmonic oscillator. So the typical Laplacians are then of the usual form. So here for n equals 2, one can take advantage of complex structures. So when I choose a complex structure, this is the Moore operator with respect to the complex structure, and that's the corresponding Laplace. And with this, we have the following expansion result, which is superficially result on resolvent expansion on the non-convex torus, so very special thing, non-convex geometry. Not all analysts like it, but you could also sell it easily to analysts, because so the situation is the following. So you have, say, a positive element in an algebra. It could as well be of a manifold a positive element in the endomorphisms of a vector bundle. You want to phrase it such that PDE people buy it. And then you look at the second order differential operator of that form. Yeah, so you have, well, a generalized Laplacian, but the symbol of the Laplacian contains a positive term which is non-commuting. I mean, if you vary points. So this is not an operator of the kind which you find normally in geometry books, where the generalized Laplacian is always one where the leading symbol is scalar. So that's a very important assumption there. So this is violated. But nevertheless, taking advantage of the twisted pseudo-differential calculus with parameters, we were able to prove an expansion result of that form. So now formally it's the same structure as before. So here, instead of a function, you take an algebra element. The heat operator is trace class, and you get an asymptotic expansion. You get, so these invariants are, well, linear in A, so you integrate over the torus, which is the trace on the torus, of course, times an invariant depending on the J parameter, which is now an algebra element. So you get a sequence of algebra elements stripped A to J, such that the heat expansion is of that form. The zeros term is, well, in conformance to the volume element, as usual, and I will talk about the second term in a second immediately. Before doing that, I want to emphasize that the similarity to the closed manifold case ends here to some extent. So as on a closed manifold, you have a sequence of invariants, the so-called heat invariants, and they are obtained in a similar way as on closed manifolds, but there is an important difference. Namely, you will get a second series of invariants showing up soon, and this is a sequence of analytic functions of multiple variables. And how do they come into play? Well, when you prove this, you have to expand the resolvent. So now, when you expand the resolvent of a two-differential operator, what you do? Well, you look for the symbol of the resolvent, and well, you multiply it as a two-differential operator with the symbol of the operator, and you want this to be 1. Now, in first order, this is the product, but then there are the subsequent terms. So you will get a system of equations that you have to solve. Well, and you have to divide by the leading symbol of p minus lambda all the time. So when the symbols commute, you can put them all on one side. In the modular case, you can't do this. So you get many expressions of the form I should say symbol of the resolvent algebra element, symbol of the resolvent algebra element, and so on and so on. And this gives an invariant which is not visible on closed manifolds for ordinary cluster operators. Although on manifolds you could see this for operators of this form. So again, you could cook up such operators also in a manifold situation. But there is actually a paper by Gierke who considered such operators some question.
I was wondering, can you also introduce a twisted connection on this Heisenberg module for which you can compare the curvature to this twisted scalar curvature term?
There is a you can. There is a natural constant curvature. Yeah. So all this is built around conformal geometry. So there is a natural constant curvature connection on the Heisenberg module. When you change the metric conformally, or when you change the metric also in the bundle conformally, you get another connection which is not constant curvature, and which and actually whose Laplacian is the operator you see there. Okay, but what about this A2? Okay, so now it's getting a bit out of hands. So now the worst part of this business is the notation, because now you have to take into account the so-called modular operator. And now, okay, so I write the k squared as e to the h, and I write nabla as up to sine commutator with h. And now comes the worst part. The modular operator is also called delta. Hang on, change. Why did you do that? Okay, so when you print it, you can use different fonts and so on. I decide, so from now on, this delta will be the modular operator, and when I really mean the Laplacian, I put the decorated Tor for the complex structure. So the modular operator is well, you conjugate by k. So okay, so this is a phenomenon which is non-commutative. You don't have it otherwise. And now, so here I write to make things not let things completely get out of hands. I just wrote here the scalar A2 term. So with Henry, I also did it in general for the Heisenberg modules. The formula a little bit more involved. So the A2 term for the Laplacian on a torus is, okay, universal constant times the trace. It's linear in A, and now the important part is what you have inside here. And now here you see the appearance of two new ingredients, K0 and H0. K0 is a function of one variable, H0 is a function of two variables, and this is something, well, it needs to be explained. So I will use on this later in the talk. So this box H is this expression. Well, it should be viewed actually in the tensor product, as I will point out later. And so you have a holomorphic function of two variables, and now this index here signifies that this acts on this on the first factor, on the second factor, whatever that means. I will use on that. And then there are now this is now just superficially shockingly complicated, and so in the first approach it was just obtained by computer aid. So you take the recursion formula for the resolvent, feed it in some computer algebra system, you press the expand button, and then you're proud that you will get more than 1,000 terms and so on, and then you get these formulas, and then you have to be ad-con to see that, well, that there is some structure behind that. And a posteriori later, we have been able to make computation completely computer-free. But of course, admittedly, this was only in a posteriori insight. And you see another important pattern here. So whatever these two functions are, there are some magic relations between them. And when you look at this here, well, this looks suspiciously familiar with with something you learn, I don't know, in second year practical mathematics, because these are divided differences. Then how do they come into play? Okay, so and they come into play through the rearrangement lemma. Okay, so this looks intimidating, but it can easily explain what happens here. So again, you have a positive element. So now here delta is always just the modular operator, and h is the log of k squared. So now suppose you have an integral of this form, and of course this here comes from resolvent powers, and all these interspersed algebra elements here in this product, they come from this recursion formula which I mentioned. And now you want to give meaning to this integral. And so now they just said, okay, so this is an analytic function of delta 1, delta 2, and so on, applied to P1 up to Bp, where this signifies that the modular operator acts on the jth factor. And I ask myself, what the heck should this mean? Is there some functional calculus behind this? And I mean, the computations are very successful by viewing this just as this analytic function. But I'm, as a more simple-minded character, I really ask, well, can I really make this rigorous in terms of some functional calculus, and maybe also contribute to this? And if you start to look at this from this point of view, you will see a lot of nice things. And this is what I try to convey in the second part of my talk. The first thing I observed is the following. When you look at the formula for this analytic function, apart from the fact whatever this function characteristic you should mean when you just give this to a smart student in your numerical analysis class when you do divided differences, you find that yeah, it's the divided difference of this function. And once you know that, all the relations between these magic functions are just a consequence of that. That's very, very convenient. And of course, this notation needs to be explained. Okay, so that's the first part of my talk, and that's how I ran into. So that's what the rearrangement lemma means, and that's how my motivation to look here a bit further. And now, for a moment, you can just pause and press the delete button. So now this is the reset button. Press the reset button. And sit back, relax, forget pseudo-differential operators, and just do functions. So, yeah, we all know holomorphic functional calculus. So I could say in advance what is not going to work when you look at this rearrangement lemma. This is not a multivariate continuous functional calculus. This won't work. So you can, what I did a couple of years ago, you can cook it up somehow you can cook up some smooth version of functional calculus to explain it, but now I prefer to do it in the holomorphic category. So okay, so take a unital Banach algebra. This is how we learn it. Take an algebra element and take an open set containing the spectrum, and take a holomorphic function in this neighborhood of the spectrum. And what you want is you want to feed the algebra element into the function. So now, what one normally just learns is, well, apply this formula, but that's not my point. So Gelfand proved something slightly different. It's just a twist, but nevertheless. So, so there is a unique continuous unital homomorphism from holomorphic functions. So this script always is borrowed from the complex analysis holomorphic functions on U into A, sending the identical function to A, and then the usual formula. So you choose a contour encircling the spectrum and integrate against the contour. It's just a consequence. And what is also a consequence is the spectrum mapping. Now, now we want to generalize it to several variables. And now this is not as straightforward as one might suspect. So normally we teach our students, well, and once you understood one-dimensional calculus, you will understand multi-dimensional calculus just in an afternoon over coffee. But here it's not as straightforward, and I will try to explain why. So the problem is the following. So you take now a Banach algebra and take commuting elements, A1 up to AN. And as before, say you have a holomorphic function of n variables in a neighborhood of the spectrum, whatever that is. And you want to plug in the variables into the function. And now, and it took quite some years from Gelfand, early 40s, until this theory was completely worked out. 25 years or so. So, and there are basically, there are basically two approaches. One, they use polynomial approximation, which is a nightmare, and there are several variables. And because in several complex variables, Not every domain is a domain of holomorphic. So and there's more concrete approach which I prefer, which you find in Borbaccio and Gamler's book. Yeah.
There's also this approach by Taylor, where you look at
J. Taylor joint spectrum.
exactly.
Yes, I wanted to avoid that. I mean, yes. So Taylor worked hard to generalize the notion of joint spectrum, but it still doesn't work in a general Banach algebra. It's just over certain Banach spaces. It's just over Banach spaces, and there is no function calculus.
There's a functional calculus in Taylor's papers.
Yeah,
Definitely so.
Okay. Okay. Anyway, so my approach is simple-minded. So so I have to. Well, maybe I have to find to do that. So the basic. Let me explain the basic idea. Which works in several variables in the one variable case. So you can take advantage of differential forms. So you choose, so you pick an algebra element, you choose a smooth function, which is one in the neighborhood of the spectrum, and then you look at this guy here, and then the simple Stokes argument shows that you can turn this integral into a two-dimensional integral, which involves this helper function, and this we can also generalize to several variables. But nevertheless, I don't want to use Taylor's spectrum. I just stick to the joint spectrum. So if you have a commutative unit of Banach algebra, you take the maximal ideal space, and then the joint spectrum is just the image of all elements in the one maximal ideal space on the tuples. And being not in the joint spectrum just means that you can linear combine the unit in this way. Yeah. And then there is a multivariate functional calculus, which is unique when you formulate it carefully. So it's so there is a unique family of continuous map from the holomorphic functions on the joint spectrum, such that for any polynomial function you get what you want to get, of course, and that's the so the following you need for the uniqueness. So when you have a holomorphic function on the joint spectrum and you artificially enlarge the number of variables, then you have this compatibility. So if you just add artificially more variables, so this little function applied to them then gives the same result. If you don't get a priori, you have this unit. But once you have done the rest, then follows. So you have all kinds of obvious. You have all kinds of properties which you would expect. Yeah, namely you have that it's a homomorphism of algebras. That if you take the product of two functions, then they behave the way one would expect. The spectrum, there is spectrum mapping property, and there is a kind of there is a composition properties. So if you have composition of maps, then the function calculus behaves nicely. Okay, so let me skip that part of the proof, but let me make a rather trivial remark, which is nevertheless of importance for the rest. So in this multivariable functional calculus, it is important that the algebra a priori is commutative. And now, so if you have a general Banach algebra and you have commuting elements, there is no immediate functional calculus for this situation. What you can of course do is just take the algebra generated by those elements. But this can be inadequate because this could make the joint spectrum too large. But the following simple-minded thing will always work, and that's sufficient for what I want to discuss then. So if you have now a non-commutative Banach algebra and you have commuting elements, and you have, say, for each of those elements an open neighborhood of the spectrum, and you have a holomorphic map in the neighborhood of that Cartesian product. So you could be way too large. So it's a strong assumption on F, so to speak. But then you can apply the multivariable functional calculus in a simple-minded way, because just by multiple contour integrals encircling the individual spectra, and it's a fact which you can easily show using Riemann sums and continuity that you really get the multivariable functional calculus which I mentioned before. Okay, so now for some nice multivariable functions. So, and for that I have to remind you of divided differences. So I'm now starting to explain the words of the title one after another. So, so start with the univariate functions, and so define iteratively what we call the divided difference. So you've seen this maybe in our classes. So F0, F is just F of X0, and then it's recursion formula. But the recursion can easily be resolved. So the divided difference of n by 1 point is this expression, which can, if the function is sufficiently regular, also rewritten nicely by the so-called Pinocchio-Amit formula in this way. So you integrate over by the simplex the nth derivative, and then you take the convex combination. Or if the function is analytic, there is also the contour integral formula. So if you have this points here, you take the contour encircling all the points, and then and now I want to view this as a function of these n+1 variables, of course. And now, so given a holomorphic function F, you now view the divided difference as a function of the x0 up to xn. And okay, so there it is. You can use it in various ways. And clearly, when you look at this formula, if the function f is analytic, the divided difference is analytic in the variables. And by what I've said before, you can also plug in commuting Banach algebra elements. So if you have a unit in Banach algebra, you have commuting elements, and you have an analytic function such that it is analytic and enabled of the union of the spectra, then there is a canonical way of talk about DDNF of with the values plugged in. And okay, so so here's the formula, and using the remarks from before, it's easy to convince yourself that it's also the multivariate functional calculus applied to these community elements. And now I need, before I come to the punchline, one more bit of notation, namely how to produce many commuting elements, also with having in the background the rearrangement lemma. Well, of course, when I have non-commuting elements, if I look at such tensors, when I put non-commuting elements in different slots in a tensor product, of course they commute. So so I therefore have to look at the projective tensor product of a Banach algebra, and I use the projective tensor product in order to be able to do the following construction. Namely, I have a natural product map from the n plus 1 tensor product times the n tensor product, which on elementary tensors is just given in this way. And now you see the pattern, of course. So you intersperse A0, B1, A1, B2, and so on. So, and this as a map works on the projective tensor product. That's just the obstacle against having a nice functional calculus, say in the continuous sense, because of course the projective. So this map here is nice and well defined on the projective tensor product, but I don't know whether it's nice and defined on the C-star tensor product. I would doubt it. But there are more experts, better experts on that. Could you do this? Could you do this construction on the C-star tensor product? I doubt it. If you could, then you would have continuous function. Okay, so now if I have now a general algebra element, I'll now look at these tensor groups and I denote by A upper J, where the A just sits in the J slot. I count the slots from 0. And now, of course, all these elements commute. And if I have arbitrary algebra elements, if I take the projective divided difference as just being, well, I apply the divided difference construction to these commuting elements and plug it into F. And when you spell it out, of course, unsurprisingly, you get this expression in the resolvent. And when you contract with B1 up to Bn, so this construction is really emphasized because it's very important. So when you have a tensor, you can contract with another tensor, which I just write as B1, contracted with B1 up to Bn. So when you do that, well, you get the contour integral, well, with this typical pattern, resolvent element, this B1 resolvent element, and so on and so on. Okay, so and here are a few applications of this. I mean, it's more an observation than really a theorem. Yeah, there is a non-dual version of Newton interpolation which now works completely schmerzfrei. So if you have algebra elements, not necessarily commuting, so now it's completely general, and you have your holomorphic function enabled of the spectrum, I mean, in the neighborhood of the union of the spectra, then this polynomial of x interpolates in this way. Okay, that's just a curiosity, so nothing in there. But then we need to continue with this to a non-trivial Taylor formula where you see things which we have seen, which you see when you work in non-trivial geometry. So there is, for instance, this Dyson expansion. Yeah? So if you look at exponential e to the a plus b, well, we know that this is the Dyson expansion, and now I just reinterpret it. Yeah, so what you see here in the Dyson expansion is, of course, just the tensor product paired with the b1 up to bn. Okay, so now in the next step, I just see that this is exponential of the convex combinations of the a upper j is paired with the b1 up to bn. Well, in the next step, applying the Rearrangement, you can translate it into this formula involving the divided difference. So you apply the divided difference of the exponential function with a0 up to n paired with the b1 up to bn. Well, okay, so it's a compact rewrite of the Dyson formula, but of course, when you look from the far left to the far right, you of course see that there is no reason anymore to specialize the exponential function. It's true in general. But also not my invention, but nevertheless, I find it rather nice. So you could think of the following problem. You have an analytic function, and so the following you can formulate the problem completely free of what I said before. You have an analytic function f. You have an analytic function f, and now you let it act by functional calculus on those algebra elements having their spectrum in U. And now this is again an analytic function, and you ask what are its derivatives. You could even formulate it in such a way that you can pose it as an exercise in your first year real analysis course. So you take an analytic function in the plane, and you look at those matrices having their spectral points in the domain of definition of that function, and now you view it as a function on the matrices, and it's again a smooth function. What is its derivative? So here's the formula. As a closed formula, completely in terms of divided differences. Yeah, so now these are algebra elements, so f of a plus b is f of a plus. Okay, so in here you have the divided difference paired with the b1 up to bn. So the nth derivative of this capital F is then apparently what you have here. You have the sum of all permutations, the divided differences with the b, the permutations of the b's plugged in. Well, before you get too enthusiastic about yourself, of course, this has been known to the Russian mathematicians long time before. So there's an old paper by Lesch and Crane in functional analysis and applications where you can find this. But nevertheless, you might ask, I mean, how do you get the ordinary Taylor series as a special case? Well, there is, as a consequence of the Rearrangement formula of divided differences, when you plug in the same elements into a divided difference, then you get, you get exactly what you expect. So that's one word. Well, you could, of course, go on and now expand this further and get, say, a full Taylor expansion in terms of the adjoint action here. You can do that in a completely different context this was popularized also by Sylvie in the paper. And now again, the rearrangement lemma. So I'm not phrasing it any differently, but now we have a full understanding of the meaning. So when you have this, well, so this just means that so when you say this signifies that and so on and so on, well, this delta j is just a modular operator in the j minus first and j's slot. So you look at this tensor product here. So this is the delta j. So and now everything is perfectly rigorous. So now these are commuting elements in a Banach algebra. And so now this is a multivariate analytic function which you apply to those, and now all this takes place in the n plus first tensor product. And all you have to do is contract. So when you write this with the dots, in fact you should read it as a tensor product. So you contract the result with the tensor product B1 tensor up to BP. And this makes it completely rigorous, and there is an immediate generalization. So you don't need these special forms here. So it works on arbitrary collection of holomorphic functions as long as the expressions you write here do make sense. Okay, so there is also a simple proof of Magnus theorem with this calculus, but I think my time's up anyway, and that's thank you.